Ladies and gentlemen and children, I'm very proud to introduce to you Wilbur. And Wilbur is a wonderful little guy, little doggy, who, and this is Wilbur, and I just wanted to show everybody Wilbur and talk about what a wonderful dog he is. And I talk a lot about DNA, I know, and I'm holding some very, very precious DNA right here. And this creature has inspired me a great deal. So I just want everyone to see Wilbur and say hello. Does that make sense?
Yeah.
You said you had questions. What questions
why do we
do you
need
have?
to trust you?
You don't need to, that's the whole point.
Okay.
You don't need to trust me at all. You don't need to trust me at all.
Why do you want other people to know you? Why do you want to take this video?
I'm not sure I do, really. That's the whole point. Maybe you can shut it off at any time. Yeah. I'm not sure I want people to know, really. I'm not sure. I'm not sure I want to be famous. You see what I'm saying, right?
Well, you could be famous.
I could be, but who cares?
Yeah, because you try to tell other people what the fact is.
Yeah, so what are the facts? The facts are they don't tell you the facts, right?
Yeah.
They don't tell you the facts. Because why? Because then they stop making money.
Yeah.
Right?
Because they don't need to tell you the facts. Otherwise, they cannot make money.
Well, there you go. See, that's exactly it, right? I did a calculation, by the way, a few weeks ago, for the omega naught cutoff. 2 root beta over m times sine 1/2 Ka. I did this calculation for DNA.
So what's that?
Well, that's a good question. This is the range that DNA vibrates in, right? Well, or any linear crystal. Remember I have the DNA?
So W is the weight.
No, that's frequency.
A frequency.
Yeah. Actually, it's angular frequency, see? Well, okay, and then I said that, well, you know, at each loop here, I had a mass. Whoops, I didn't draw that very well. At each loop, I had I call this
spring.
Yeah, that's a spring, and then at this loop, I have another mass, right? So I added up all of the insides here, and I came out with a number. I came out with a number, I'll say 800 atomic mass units. And of course I put that down there. Well then beta, I stole that from sodium chloride. My beta is a sodium chloride crystal elastic constant, which worked out to be 6.93, I think, times 10 to the 5 kilograms, and then it'll be seconds to the -2. So then when I take the 800 and put it in here times 1.66 times 10 to the -27 kilograms, and I take the square root of that and multiply it by 2, I came up to it 1.39 times 10 to the 15 hertz, which is about the cutoff frequency for a solid, for a crystal. So I came up kind of close. I didn't show all my arithmetic, which I apologize for, but my cutoff frequency is about right, according to what I read. But again, the calculation is not so good because I stole the spring constant from sodium chloride. This is not sodium chloride, but what the heck, right, you know.
But
Yeah.
why would it vibrate? do you use any medicine or do you?
Why does this vibrate?
Yeah, because you are telling us the frequency,
Yeah.
and so why don't you think that is it still? I mean, is it
Why does it vibrate?
in a steady situation?
Well, it has to vibrate.
It has to be vibrating.
It has to vibrate because the nature of this, well, like I said before, I said a couple lectures ago, if you want to call them lectures, if you take the carbon-carbon bond, this is actually a spring, okay? In the carbon-carbon bond, you've got vibration here, see? So that you can see in all of these, you know, this is sugar phosphate, you're going to have this springing action. It'll be all through this crystal. This is a crystal again.
So even though he's healthy, the DNA still vibrates.
Well, see, that was the whole thing. You see, if the DNA is healthy, that will mean M won't be 0. If M is 0, then this thing will go to infinity. You won't have any vibration. So that, yeah, the healthy DNA has got to have some vibration. And when when K is equal to pi over A, at the cutoff, when K is equal to pi over A, when this is vibrating at its maximum, then this vibration will be the order of 10 to the 15. Now, of course, this vibration is called, I believe it's vibration in the normal mode. It's not the optical mode, it's the normal mode, you see. That normal mode means that it's sort of vibrating all together. See? But actually, it doesn't really vibrate that way all the time because it's vibrating like this too. See? This back and forth. Opposite this way is the optical mode, which is a higher frequency. So it's vibrating like this in the normal mode, but in the optical mode, at the same time, it's...
If this is related with the frequency, and but if I use any music, then I can, if I use music and then I can vibrate the DNA.
I don't think it's not going to hear your music. I don't think this is the same kind of thing. I don't think it's going to hear the music at all.
If I use a suitable frequency, and for example, sound.
10 to 15, you don't have that. I don't think you could generate anything that high. See? So this frequency is really, really high. We don't have anything yet that will generate frequency that high. The point I'm trying to get at here, though, is this frequency is related to the genetic code, to the genetic transfer of information. That's the point I'm getting at here, is that these vibrations throughout the DNA have got to influence the genetic coding system, which is, again, DNA, RNA, protein, you see? Because I'm saying in this model that I can approximate the DNA vibrations with this spring, you see, so everything I derive for this spring system, I'm saying the DNA behaves in a similar manner, see? That's the idea behind this model. See, this spring thing is a model. DNA is not exactly this spring, but it's the best I can cook up right now. Hopefully in a couple weeks I can cook something better up. But I've been busy lately and I haven't had time to work on this too much. But that's basically it. This calculation, that's today's show. And Wilbur, of course. Today's show we could call the Wilbur Lecture in Physics. The Wilbur Lecture in Physics. the Wilbur, whoops, that doesn't look good. The Wilbur lecture in physics. In physics. See, so today's calculation was this cutoff frequency, right? Like that. Just to give you some idea of how fast this is vibrating. This is a tremendously high frequency. What is it? 10 to the 9 times 10 to the 6. So that's 1 million times 1 billion.
So what kind of theory do you want to develop?
That's a good question. Yeah, I don't know where I'm going yet. Last time I said quantum field theory, remember? I want to develop a quantum field theory for this. But where that quantum field theory goes, I don't know. But I believe one can be developed. Because again, I've got p squared over 2m plus the potential energy k, let's say, x, what is it, L minus x, L plus 1, say, that kind of thing. Once I have the kinetic energy and the potential energy, then I can develop this thing. I haven't done it yet, but I'm gonna. Maybe tomorrow. Well, not the whole thing tomorrow, but you see. Oh, yes. And then, of course, from that, maybe we can talk about, like I said a minute, we excite this DNA with a compound. The compound that I use excites the DNA, and then, of course, the DNA kicks out information, like according to this, you see, it sends out information, and this information will be quantized. That's the quantum field theory. So the genetic code is quantized, see? The genetic code is quantized. The genetic code is quantized, see? But even Mendel said that. Mendel said that in 1866, right? That if you can only get, if you put in a certain amount of information, you only get a certain amount of information out. Finite here, finite there, right? There isn't, you don't put in, say, 2 parts and you get out half. You have to get, well, you put a certain amount in here and you get a discrete amount out. It can't be you cannot get half, let's say you can't get half of an information bit, let's say, see? So whatever goes in here has got to come out in a quantized way.
You see, your contribution is in this structure. I mean, you have tried to describe the DNA structure, and is this your invention?
No, I think other people do this as well. Other people do this kind of thing.
Okay.
But I haven't read their papers yet. But this is my idea, based again on this compound that I've been testing for several years now. And again, the data, DNA, RNA, protein, see? Right? Because I know how to cure infection.